Welcome back. We're diving back into the world of mathematics today.
Always exciting.
This time we're going to be looking at the math behind something we use every single day.
Uh, Let me guess.
Electric currents.
Makes sense. We do rely on those quite a bit, don't we?
We do. We've got some great sources to help us out too.
Oh, yeah? Like what?
We've got Wikimedia entries on antimeters, electric currents, and Ohm's law.
Nice. Those are always helpful.
And on top of that, we've got this really neat analogy for explaining electric current.
Cool. I'm always a fan of a good analogy.
Me too. I think these sources are going to lead to some pretty electrifying insights.
I'm sure you're right.
I hope our listeners are ready to have their minds blown. But before we get ahead of ourselves, let's start with the basics. What exactly is an electric current?
Well, at its simplest, it's the flow of charged particles. And this flow, it allows them to do work power things.
I see. So it's not just the charged particles themselves, it's the fact that they're moving that makes them useful.
Exactly. Think of it like a river. The water molecules are like charged particles, and the more water flowing in the river, the stronger the current.
Okay, so the more charged particles flowing, the stronger the electric current. That makes sense.
Right. And just like we measure the flow of water in, say, gallons per second, we need a way to measure electric current.
And that's where the ampere comes in.
You got it. The ampere, or amp for short, is the unit of measurement for electric current.
Right, and I remember it's named after André-Marie Ampère, a French physicist.
That's right. But the name isn't just a tribute. The ampere is actually based on a precise definition.
Okay, so what exactly does an ampere represent?
Well, for a long time, it was defined by the magnetic force created between two parallel wires that were carrying an electric current.
Oh, wow, I never thought about it like that. So, like, if you held two live wires side by side, the force you'd feel between them that was used to define the ampere.
Pretty much. It's a very, hands-on kind of definition.
That's really interesting. But I also read somewhere that the definition of the ampere has been updated recently.
You're right. In 2019, they redefined it.
So what's the new definition based on?
They decided to redefine it in terms of a fundamental constant in physics, the elementary charge.
The elementary charge. I'm not familiar with that one.
It's the charge carried by a single proton.
Oh, I see. So instead of using a physical measurement of force, they're now basing it on something more, I don't know, fundamental to the nature of electricity itself.
Exactly.
That makes a lot of sense. So does that mean an ampere is basically like counting a certain number of protons flowing past a point each second?
Yeah, you could think of it that way. It's a huge number, mind-bogglingly large, actually. But the main point is that now we have this super precise and standardized way to measure electric current.
That's fascinating. So we've got our flowing charged particles and a way to measure that flow. I'm guessing this is where Ohm's law comes in.
You're on the right track. Ohm's law is all about the relationship between the current flowing through a conductor, the voltage that's pushing those charges, and the resistance that's working against that flow.
Okay, so can we go back to the river analogy for a second?
Sure.
Would voltage be like the steepness of the river? Like the steeper the river, the faster the water flows?
That's a great way to think about it. And resistance, that would be like the rocks and obstacles in the river, slowing down the flow.
I see, I see. So a steeper river with fewer obstacles means a faster flow, just like a higher voltage and lower resistance result in a stronger current.
Precisely. And this relationship, it's captured in a really simple formula. V equals IRV for voltage, I for current, and R for resistance.
That's right, Ohm's law. I remember that from our notes. It seems so simple, but I imagine it must be incredibly powerful.
Oh, it absolutely is. It's like the bedrock of circuit design. It lets engineers figure out how to control the flow of electricity in all kinds of devices.
So you're saying that everything from the wiring in our homes to the super complex circuitry in smartphones, it all comes down to this one equation.
That's right. Ohm's law really is fundamental to how we understand and use electricity, but it's not just for simple circuits either.
Oh, this is where it gets even more interesting.
You bet. We can apply Ohm's law to some super complex systems too, things like power grids even.
Wow, that's incredible. So the same basic principle applies to something as small as a circuit board and something as massive as a power grid.
You got it. But it goes even further than that. We can even apply it to the flow of electrons within individual atoms.
Wait, really? You're saying the same math used to design a power grid can be applied to something as tiny as an atom?
Exactly. And that's part of what makes math so amazing. It reveals these underlying patterns and connections that exist across completely different scales.
That is mind-blowing. So Ohm's law isn't just some abstract formula in a textbook. It's a fundamental principle governing how electricity flows on every level, from the macroscopic down to the microscopic.
That's a great way to put it.
So we've been talking about Ohm's law on like a bigger scale, circuits and power grids and stuff. But you mentioned that it can also be applied to individual atoms. I'm curious, how does that work exactly?
Well, physicists use a more kind of a generalized form of Ohm's law to study materials at that atomic level. They're looking at things like conductivity.
Right, conductivity, that's how easily electricity flows through a material, right?
Exactly. And when we zoom into this tiny level, like the atomic level, we can analyze something called current density.
Current density, what's that?
It's basically a measure of the current flow per unit area.
Okay, so instead of just looking at the total current flowing through a wire, like we were talking about before, with current density, we're looking at how much current is squeezed through a tiny, like, cross-section of that wire.
You got it. Think of it like comparing a narrow, crowded highway to a wide open one. The number of cars passing a point per minute might be the same on both, but the density of cars on that narrow highway, it's much higher.
Okay, that's a good analogy. So Ohm's law can help us understand the flow of electricity at both the macroscopic and microscopic levels. That's amazing. But earlier you mentioned something about heat conduction, too. I'm curious, is there a link between electricity and heat?
There is. It's actually really fascinating. The same mathematical principles that govern the flow of electricity, we can also apply them to the flow of heat.
Wait, really? But heat and electricity, they seem so different. I mean, heat's about temperature, and electricity is about the flow of charged particles. How can the same math apply to both of them?
I know, it might seem counterintuitive, but the key is understanding that both phenomena involve a flow that's driven by a difference in potential.
A difference in potential.
Yeah. So in an electrical circuit, it's the difference in electrical potential or voltage that drives the flow of electrons, right? But in heat transfer, it's a difference in temperature that drives the flow of heat energy.
I see. So just like electrons flow from a point of high voltage to low voltage, heat energy flows from a region of high temperature to low temperature.
Exactly. And the rate of that flow, it's determined by the material's properties. So in electricity, we're talking about resistance. But in heat transfer, it's thermal conductivity. A material with high resistance is going to impede the flow of electrons, just like a material with low thermal conductivity resists the flow of heat.
So even though the underlying mechanisms are different, like electrons flowing in one case and heat energy flowing in the other, the mathematical relationships governing those flows are surprisingly similar.
That's the beauty of math, isn't it? The same equations can be used to model and predict these seemingly unrelated phenomena.
That's a really remarkable insight. It makes you realize that math is more than just numbers and formulas. It's like a language that describes the fundamental principles governing the universe.
I like that. A language for the universe, and it's this underlying mathematical structure that allows us to make these connections and draw insights that we might not otherwise see.
Okay, you know what? Now I'm looking at my phone, my laptop, even the walls around me, and I'm seeing them in a whole new light. All this hidden math, all these equations governing the flow of electricity all around us. It's kind of mind-blowing. But our outline also mentions something about superconductivity. I'm wondering, where does that fit into all of this?
Ah, yes, superconductivity. Now, this is where things get really interesting. And it actually kind of challenges our understanding of Ohm's law a bit.
Oh, how so?
Well, you're talking about those materials that can conduct electricity with zero resistance, right?
Right. Superconductors, I remember reading about them, but they always seem so, I don't know, sci-fi.
I know what you mean. They might sound like science fiction, but I assure you they're very real. And they really push the boundaries of our mathematical models.
Well, because if resistance is zero, then in that equation V equals IR, any voltage would result in an infinite current, right? And that doesn't seem physically possible.
You're exactly right. The traditional form of Ohm's law, it just doesn't quite work when we enter the world of superconductivity. And this really highlights how even our most fundamental equations, they have limitations. And they need to be adapted as we make new discoveries, as we encounter new phenomena.
So does that mean that all our equations are wrong when it comes to superconductors?
Not necessarily. It's not that the math itself is wrong. It's more that it needs to be applied differently in those situations. Superconductivity involves quantum phenomena, and those aren't fully captured by the classical form of Ohm's law.
So we need new physics, new math to fully understand superconductivity.
In a way, yes. Scientists are constantly working on new models and equations to describe and predict the behavior of superconductors. It's a very active area of research.
That makes sense. It's a good reminder that science and math, too, they're always evolving. As we make new discoveries and push the boundaries of our understanding, we need to adapt our models and equations to keep up.
Precisely. There's always more to explore and learn. And often it's the unexpected discoveries, the ones that challenge our existing models, that lead to the most groundbreaking advancements.
Well, this has certainly been an eye-opening deep dive into the math of electricity. I never realized that something we take for granted every day could be so complex and fascinating.
And we've only scratched the surface.
Sounds like we need a whole other deep dive just to cover superconductivity.
Yeah, we could probably spend hours talking about that.
But even without going too deep into superconductivity, I think we've learned some pretty incredible stuff about the math behind electricity.
I think so too.
It's amazing to think that the same mathematical principles can explain the flow of electrons in something tiny like a microchip and in the huge currents that power our cities.
Right, and we can't forget about the connection to heat flow.
Oh yeah, that was a surprise.
It really shows how math can reveal these hidden patterns and connect things that seem totally different at first glance.
It's like math is a secret code for understanding the whole universe.
I like that. It's true. Math gives us the tools to understand everything from tiny atoms to giant galaxies.
It's definitely given me a lot to think about.
Good.
Next time I flip a light switch, I'll be thinking about all the stuff we talked about. The charges flowing and the voltage and all those equations.
And maybe you'll even think about superconductivity and how it pushes the limits of what we know about electricity.
I will. This has been a fascinating look at the math of electric currents.
I agree.
Thanks for sharing all this amazing information with us.
My pleasure. It's been fun.
I hope everyone listening learned something new today about the hidden world of math that's all around us.
Me too. And remember, there's always more to learn, so stay curious and keep exploring.
That's great advice. And that's it for this deep dive into the world of mathematics. We'll see you next time.